Hello friends, this is Group 2. We are going to present our video on slip line field theory. So let us now introduce the concept of slip line field theory. Slip line field theory is used to model plastic deformation in plane strain only for a solid that can be represented as a rigid plastic body. Elasticity is not included and the loading has to be quasi-static. This method has been recently largely superseded by finite element method. But this theory can provide analytical solutions to a number of metal forming processes and utilizes plots showing the directions of maximum shear stress in a rigid plastic body, which is deforming plastically in plane. Let us now define what is a slip line. A line generally curved which is tangential all along its length to directions of maximum shear stress is known as a slip line. Now what is a slip line field? Slip line field is a complete set of orthogonal curvilinear slip lines existing in a plastic region. And this is a diagram showing slip line field model where alpha and beta are orthogonal field lines. Let us now look at the assumptions where slip line field theory is valid. Plane strain deformation. We all know what is a plane strain. A plane strain is a condition where epsilon z is equal to 0. Quasi-static loading. This means there is a constant shear stress at interfacial boundary. Usually either a frictionless condition or a striking friction is assumed. No temperature changes are considered. No body forces are required. The solid is idealized as a rigid plastic Mises solid. Well, this implies that the neglect of elastic strain and treats the flow stress as constant. This diagram shows the plane strain condition. We now look at the Mohr circle diagram for stress in plane plastic strain. The state of stress at any point in the deforming material may be represented in the Mohr circle diagram. In this diagram, P shows the hydrostatic pressure, K shows the pure shear strength, sigma 1, sigma 2, sigma 3 are principal states of stresses, whereas A and B represent the stress states at a point on planes parallel to the slip lines through that point. Now let us define what are slip lines in slip line field theory. These are the alpha and beta lines. The slip lines consist of a curvilinear mesh of two families of lines which always cross each other at right angles. By convention, one set of lines are named as alpha slip lines and the other are called beta lines. As you can see in the diagram, alpha lines and beta lines intersect each other at right angles to each other. Now let us look at the conventions used to distinguish between alpha lines and beta slip lines. The slip lines are labeled alpha and beta as indicated in the figure below. It is essential to distinguish between the two families of slip lines, and the usual convention is that when the alpha and the beta lines form a right-handed coordinate system of axis, then the line of action of the algebraically greatest principal stress sigma 1 passes through the first and the third quadrants. The anti-axis clockwise rotation theta of the alpha line from the chosen axis is taken as a positive. Here P is hydrostatic pressure, which is orthogonal to the slip line, and K is the pure shear strength, which is tangential to the slip line. Now we look at the load necessary for a particular plastic forming operation. In order to determine the load necessary for a particular plastic forming operation, first of all, the slip line field patterns must be obtained. This means that the equations for the variation of P along both the alpha and beta lines must be derived. Also, we must check that all velocity conditions along alpha and beta lines are satisfied. Here we require the magnitude of P, that is the hydrostatic pressure, and the direction of K, that is the pure shear strength, to determine the load necessary for.
Now we shall derive stress equation for determining magnitude of P and K. The equations of equilibrium for plane strain with neglect of body forces are d sigma x by dx plus d tau xy by dy equals to 0 and d tau xy by dx plus d sigma y by dy equals to 0. These equations are basic equations. The above stress components sigma x, sigma y, tau xy expressed in terms of P and K are sigma x equal to minus P minus K sin 2 phi, sigma y equals to minus P plus K sin 2 phi, and tau xy equals to K cos 2 phi. P is the normal or hydrostatic pressure on two planes of yield shear stress. Differentiating and substituting from equation 2 in equation 1, we have the following equation. If now the alpha and beta lines are taken to coincide with 0x and 0y at 0, that we take phi equals to 0, equation 3 become minus dp by dx minus 2k d phi by dx equals to 0 and minus dp by dy plus 2k d phi by dy equals to 0. Thus integrating the previous equation, that is equation 4, we get p plus 2k phi equals to f1 which is a function of y plus c1 and p minus 2k phi equal to f2 which is a function of x plus c2. If the hydrostatic stress P can be determined at any point on a slip line, for example at a boundary, it can be deduced everywhere else. Thus, P plus 2k phi equals to constant along an alpha line, P minus 2k phi equals to constant along a beta line. The equations 6 are known as Henke equations and are equivalent to the equilibrium equations for a fully plastic mass stress in plane strain. In general, the values of constant C1 and C2 from equation 5 vary from slip line to. Now let's try to understand the boundary condition at a free planar surface. Let us say the free surface is a plane with normal in the y direction. Then y stress and the xy shear stress are 0. We can understand it clearly from the following figure. This figure shows plane strain indentation. Here OC is free surface, hence sigma y and tau xy equals to 0 at this free surface. CB is the alpha line and OB is the beta line, and both the lines are perpendicular to each other. However, this figure shows one of the possible stress fields in a plane strain indentation. However, other stress fields are also possible.
Now from Mohr circle we know that sigma x equal to minus p minus k sin 2 phi and sigma y equals to minus p plus k sin 2 phi and tau xy equals to k cos 2 phi. Now from the above given boundary conditions, sigma y equals to 0 and tau xy equals to 0. Now if we put tau xy equals to 0 in third equation, we get phi equals to plus minus 40. Now we put phi equals to plus minus 45 degree in the equations to get the following results as sigma x equals to minus p plus minus tau naught, sigma y equals to minus p plus minus tau naught equals to 0 and tau equals to 0. Now since sigma equals to 0, hence hydrostatic stress at free surface must be plus minus tau naught and sigma x equals to 2 sigma h equals to plus minus 2 sigma 2. Now let's take another condition where sigma y is not equals to 0. Here y direction is normal to a surface and the xy shear is again assumed to be 0. Hence the alpha beta line must again be at 45 degree to the surface. We now have sigma x equals to sigma h plus minus tau naught and sigma y applied equals to sigma h plus minus tau naught and tau equals to 0. So the hydrostatic stress at the loaded surface must be sigma h equals to sigma y applied plus minus tau naught and x stress is sigma x equals to sigma y applied plus minus tau naught. Here from above two boundary conditions we can see how does Henke net look like near a shear free plane surface. Henke net is just a net of alpha beta lines. Here in this diagram OC is free surface and here Henke net in this region OCB consists of straight alpha beta lines as we can look from this diagram. Now let us take an example to use what we have learned so far. In the figure given below, we have a semi-infinite slab and a force P perpendicular that is applied to an indenter which is applied on O dash. We can propose a slip and field as given in this figure. Here from the method described before, we can determine alpha beta lines as shown in the figure. Here CB is alpha line and OB is the beta line. Here indenter is in between O dash. Now we are assuming a well lubricated indenter, so the shear over O dash is 0. Now in the free surface OC, from the boundary conditions described before, sigma y equals to sigma 1 equals to 0, sigma 2 equals to minus k, and sigma equals to minus 2k. Here sigma 2 is equals to hydrostatic pressure. We can also draw Mohr circle of stress for a point on this free surface. Now for sigma to O dash, we require change in phi from C to O dash along the alpha line. For delta phi, rotating clockwise along CBA O dash on alpha, we get phi equals to pi by 2. So delta phi equals to minus pi by 2. Hence we get sigma 2 OO prime equals sigma 2 OC plus 2k delta phi alpha. Now sigma 2 OC equals minus k I derived before, so we get minus k plus 2k into minus pi by 2. Now P perpendicular upon 2k equals PO upon 2k, which equals to minus sigma 2 OO upon 2k, which equals 2.57. Now with both von Mises criteria, 2k equals 1.155y, so P perpendicular equals 2.97y. So P perpendicular is approximately equals to 3 times the yield strength. Thank you very much.